Hello everyone. In the previous lecture, we have introduced the compressibility of soil and the fundamentals of consolidation. We know compression and consolidation are important to the settlement determination. So, how to determine the compressibility of soil in the lab? One-dimensional consolidation test is a common method. This section, we will talk about this test and its interpretation. The characteristic of soil during one-dimensional compression can be determined by the oedometer test. This picture shows the oedometer, which include loading system, oedometer cell, and dial gauge. The soil specimen is placed in oedometer cell. The load on the specimen is applied through a lever arm, and the compression of the specimen and the pressure is measured by a dial gauge operating on the loading clamp. In one-dimensional consolidation test, the specimen is placed inside a metal ring with two porous stones, one at the top of the specimen and another at the bottom. The confining ring imposed a condition of zero lateral strain on the specimen. The specimens are usually 2 centimeters height and 30 square centimeters in cross area. The saturated specimen is kept under water during the test. The purpose of oedometer test is to get the load deformation curve. When we apply the load to the soil specimen in the oedometer test, the initial pressure will depend on the type of soil. Then a sequence of pressure is applied to the specimen. Each load usually is kept for 24 hours. In exceptional cases, a period of 48 hours may be required. Compression readings being observed and suitable intervals during this period. The sample heat decreased from initial heat H0 to H1 and the pressure sigma 1. And at the same time, the water ratio of specimen decreased from E0 to E1. After that, the load usually is doubled, which doubles the pressure on the specimen, and the compression measurement is continued. The general shape of the plot about the deformation of the specimen against time for a given load increment is shown in this figure. From the plot, we can observe 3 distinct stages. Stage 1, initial compression, which is caused mostly by preloading. Stage 2, primary consolidation in this stage. Extra water pressure gradually is transferred into effective stress because of the expulsion of pore water. Stage 3, secondary consolidation, occurs after complete dissipation of the extra water pressure. Some deformation of the specimen takes place because of the plastic readjustment of soil fabric. After the time deformation plots for various loadings are obtained in the laboratory, it's necessary to study the change in the water ratio of the specimen with pressure. Let's assume the soil is homogeneous and saturated. The soil particles and the water are incompressible. Vertical flow of water and the validity of Darcy's law. According to the phase diagram, we can calculate the initial water ratio of the specimen E0. For the first increment loading, which causes a deformation delta H1, calculate the change in the water ratio delta E1 in this equation. Delta H1 is obtained from the initial and the final dial reading for the loading. Then calculate the new water ratio E1 after consolidation caused by the pressure increment. Until the end of consolidation, total stress is equal to effective stress. For the next loading, sigma 2, please notice sigma 2 equals the cumulative load per unit area of specimen. It causes additional deformation delta H2. The water ratio until the end of consolidation E2 can be calculated under this equation. Proceeding in a similar manner, we can obtain the water ratios until the end of the consolidation for all load increments. So we know soil volume deforms delta H due to increment of loading delta sigma. At any time, effective stress on the soil sample is equal to applied stress on the soil. The effective stress and the corresponding water ratio E until the end of consolidation are plotted. The relationship curve is called compression curve, which can be plotted as EP curve or log P curve. The typical shape of such plots are shown in these figures. Sometimes the expansion of the specimen need to be measured under successive decrease in applied pressure. The compression curve reflects the compressibility characteristic of soil. This figure shows the oedometer test results for two different soils. It can be seen under the same incremental pressure, the change in water ratio of curve A is greater than that of curve B. This means the compressibility of soil A is higher than soil B. Therefore, the slope of the compression curve can be used to estimate the soil compressibility. So, we can define the coefficient of compression alpha. The steeper the compression curve, the greater the coefficient of compression will be. The unit of coefficient of compression is the inverse of pressure. However, the coefficient of compression is not a constant. It's closely related to stress level. In engineering practice, it's common to use the coefficient of compression in the range of 100 kPa to 200 kPa to estimate the compressibility of soil. The larger the coefficient of compression, the more the soil can be compressed. Usually, when the coefficient value is less than 0.1 inverse of megapascal, soil is low compressible. When the coefficient value is between 0.1 and 0.5, soil is intermediate compressible. If the coefficient value is greater than 0.5 inverse of megapascal, soil is high compressible. In general, for intermediate compressible soils, especially for high compressible soils, cautions and measures should be taken for the structures against large foundation settlement. In addition to the coefficient of compression, we can define other compression parameters based on EP curve. MV is the coefficient of volume compressibility, which represents the volume change per unit volume per unit increase in effective stress. Under zero lateral strain condition, MV represents the volume change per unit thickness per unit increase in effective stress. The unit of coefficient of volume compressibility is the inverse of pressure. According to the definition of coefficient of compression alpha, we can get the relationship between alpha and MV. The value of MV for a given soil is not constant, but depends on the stress range over which it's calculated. Moreover, we can define constraint modulus of compression, ES, based on EP curve. ES represents the ratio of vertical stress to vertical strain. Under zero lateral strain condition, according to the base relationship, ES can be expressed in coefficient of volume compression MV. It's clear that constraint modulus of compression ES is the reciprocal of coefficient of volume compression MV. So, the unit of ES is the pressure. The value of ES reflects the capability of the soil resisting against compressive deformation under one-dimensional compression. Let's summarize the compressibility parameters based on EP curve. We can define coefficient of compression alpha, coefficient of volume compressibility MV, and constraint modulus of compression ES. This chart shows you the relationships among the three parameters. Thank you for watching.